Okay, so today I will help myself with animation of the control ventilation by Alia Medical Media. Please like this video and subscribe to the original, of course. And as always, I will stop from time to time to stress what is the most important and to explain more difficult parts. So let's start.
Breathing is mostly an involuntary automatic process. Because its major function is to supply the body with oxygen and remove carbon dioxide, the rate and depth of breathing is generally regulated by carbon dioxide status or the need for oxygen. For example, breathing...
So obviously, breathing is in order to increase levels of oxygen, decrease levels of carbon dioxide. If you have too much of the carbon dioxide or not enough of the oxygen, we need to breathe more. If we have enough of the oxygen and not too much of the carbon dioxide, we do not need to breathe more. One more time, negative feedback loop, as everywhere, as always, in the organism.
Automatically accelerates with physical exercise when the body's need for oxygen is increased. Basically, various receptors in the body feed information about its metabolic state to the respiratory center in the brainstem, which responds by changing the firing pattern of inspiratory and expiratory neurons. Inspiratory neurons fire during inspiration, while expiratory neurons only fire during deep expiration, since quiet expiration is a passive process.
Okay, so here the important thing also that although obviously this center is regulating everything, the most critical thing to, at least from our perspective, to understand is what is affecting this center in the brain. So from what sources it gets information and what activates it and what inhibits it. So for the rest of the video, concentrate on this. Yes. So what activates this center in the brain? So it's also what would activate the ventilation, and what inhibits it.
The fibers of these neurons descend to the cervical and thoracic spine, where they synapse with motor neurons. Motor neurons then travel in several nerves to respiratory muscles, changing the way these muscles contract, adjusting thereby the rate and depth of breathing to suit the body's needs.
So I suppose it's quite obvious, yes? These are just ordinary motor neurons that innervate our respiratory muscles.
Of most importance are phrenic nerves, which control the diaphragm, and intercostal nerves, which innervate intercostal muscles. While the functional anatomy of human respiratory center is complex and not entirely clear, the current consensus is that the primary center is composed of several areas in the medulla. The dorsal respiratory group, DRG, mainly associated with inspiration, the ventral...
Okay, let's not delve into too much detail. Okay.
These are detected by chemoreceptors. Central chemoreceptors located on the surface of the medulla monitor pH changes in the cerebrospinal fluid.
So this is very important. Thanks to those chemoreceptors in the brain, the respiratory center can extremely fast, can enable extremely fast responses to changing carbon dioxide levels. In case of the brain, it's mainly about the carbon dioxide. The oxygen is not so important in those receptors.
Peripheral chemoreceptors found in the aortic and carotid bodies respond to fluctuations in pH, carbon dioxide, as well as oxygen levels in the blood.
Yeah, so they are a bit different, yes, as you can see, because also the oxygen. About the pH and carbon dioxide, they are strictly connected. As we had told a lot of times, yes, we have carbon dioxide reacts with water to create the carbonic acid. So obviously, more of the carbon dioxide, the acidity rises, so the pH drops.
Peripheral receptors transmit signals to the respiratory center via the vagus and glossopharyngeal nerves. An increase in carbon dioxide, such as during exercise, causes a decrease in pH, which is sensed by central or arterial chemoreceptors and leads to deeper, faster breathing. More carbon dioxide is exhaled, and blood pH returns to normal. The respiratory center also receives input from various mechanoreceptors in the lungs, which transmit information about the mechanical status of the lungs via the vagus nerve. For example, pulmonary stretch receptors present in smooth muscle of the airways are activated when the lungs are excessively inflated and trigger the inflation reflex, which stops inspiration and prolongs expiration.
So when the lungs are stretched too much, we do not want to stretch them more. One more time, negative feedback loop. Yes. So if we do not want to overstretch the muscles, generally the lungs, yes, and everything connected, we need to have a mechanism that would prevent this overstretching. And as you can see, we have.
Other receptors respond to inhaled irritants and are responsible for defensive respiratory reflexes.
So what are the irritants? Irritants are everything that generally if you breathe in would make you cough. Yes, just to make it simple. So everything that is potentially harmful for our lungs, we want to get out, and we do not want to get in. So all of our airways would constrict in order to reduce the amount of the substance, the potentially harmful substances that will get deep into the lungs. Yes, these are the irritants, at least from perspective of our body,
such as bronchoconstriction or coughing. The limbic system and hypothalamus also send information to the respiratory center and allow pain and emotional state to affect breathing.
So, for example, in case of the panic attack, the respiration rate can increase very much, although there is no need for it. Yes, the levels of the oxygen are usually okay. The levels of carbon dioxide are usually okay, but because of those emotions, people are respirating, so ventilating too fast.
For example, pain or strong emotion may induce gasping, while anxiety may cause uncontrollable hyperventilation. While breathing is mostly involuntary, some degree of voluntary control is possible, for example, during singing, playing wind instruments, or holding breath underwater. In this case, the control originates from the primary motor cortex, which sends signals directly to the spinal cord, bypassing the respiratory center in the brainstem. There are limits, however, to the extent one can control their breath, even though it's possible to increase these limits with training.
Okay, so thank you very much. Please like the video because they are really making a good job. And okay, it's enough for today. Thank you very much.